Okay, let's unpack this. Think about how incredibly intricate our computers have become.
Hmm.
We're talking about data moving at mind-boggling speeds between all sorts of sophisticated components, and right at the core of this digital ballet are high-speed connections like PCIe.
Yeah, absolutely central.
Now picture this. At these speeds, even a tiny fleeting error, a single bit flipped at the wrong moment, could cause chaos. We could see corrupted data, system crashes,
Oh, yeah.
and in critical environments like servers and data centers, the fallout can be massive.
Absolutely. In those mission-critical scenarios, what we call RAS, reliability, availability, and serviceability, is paramount.
Hmm.
Even brief glitches or data hiccups can lead to significant financial losses, operational disruptions.
Right.
That's why the underlying technologies have to be incredibly robust, especially when it comes to how they handle errors.
Which brings us to today's deep dive. We're going to plunge into the fascinating world of PCIe, error detection, and handling.
Good stuff.
Think of it as exploring the immune system of your computer, constantly on guard, identifying threats, and trying to neutralize them before you even notice a problem.
Exactly. Whether you're a tech enthusiast, curious about the inner workings, maybe a pro prepping for a technical discussion, or just someone who's experienced the occasional system weirdness and wondered why.
We've all been there.
Right. Understanding PCIe error management offers you a really valuable perspective on the unseen work that keeps everything humming along.
So what's our mission today? We're going to dissect the ingenious ways PCIe spots errors. It's like having multiple security checkpoints. We'll explore the different categories of errors it can identify, from the ones it can resolve on its own to the more serious ones that require a bit more attention.
The different flavors of trouble.
Exactly. And we'll delve into this advanced error reporting system, AER, which gives us an incredibly detailed look under the hood.
Yeah, that's key for diagnostics.
Our source material for this exploration, a comprehensive analysis of PCIe error detection and handling. Ready to get started?
Let's do it. The first key to understanding PCI's resilience is its layered architecture. Think of it like a defense-in-depth strategy,
Okay.
with error detection mechanisms built into the physical layer, the very foundation, then the data link layer, and finally the transaction layer. Each layer has its own specific job and its own ways of checking for problems.
Okay, let's start at the base, the physical layer. This is where the raw bits are actually transmitted, right? What kind of errors are we looking at down at this fundamental level?
Well, at the physical layer, the focus is really on the integrity of the electrical signals themselves.
Yeah.
We're talking about things that can distort or corrupt the signal as it travels. Issues with signal quality, maybe errors in how the symbols representing data are encoded.
Like that 8B, 10B stuff in older PCIe.
Exactly. AB10B decoding errors. That was a method used to ensure enough signal transitions for clock recovery. And error there means, well, those basic signal rules were violated. Or maybe problems with the framing of the data. Even subtle timing mismatches, handled by things called elastic buffers, they compensate for slight clock speed differences. Issues there can be flagged.
So it's really about the raw signal quality.
Pretty much. While the physical layer doesn't always directly fix these issues, it's the first line of defense in noticing that something isn't quite right with the basic transmission. Receiver errors are a type of correctable error that can actually originate at this stage.
So if the physical layer senses something is off, it raises a red flag to the next level up. That's the data link layer. What's its role?
Right. The data link layer is really the workhorse for reliable communication between two directly connected PCIe components. Its main job is making sure data gets from point A to point B on that single link without corruption or loss.
How does it do that?
Through several clever mechanisms.
Yeah.
First is the link cyclical redundancy check, or LCRC.
Okay.
For every transaction layer packet, or TLP, that's the packet carrying the actual user data, the sender adds a 32-bit CRC. Think of it like a digital fingerprint. The receiver checks the CRC to make sure the fingerprint matches. And this is hop-by-hop protection, ensuring nothing slips through on that one specific link.
Okay, so like a digital fingerprint that confirms the data arrived intact at each step. What else does the data link layer do?
It also uses sequence numbers. Every TLP gets a unique number so the receiver can spot if any packets are missing or maybe if they've arrived out of order.
Ah, smart.
Then there are the data link layer packets, or DLLPs. These handle the housekeeping of the link, things like acknowledgements, flow control updates.
Right.
And these DLLPs have their own CRC check too, usually 16-bit, just to make sure those control messages are okay.
And this is where that crucial ACNK protocol comes into play, right? The one that sounds like a digital thumbs up or thumbs down.
Precisely. Yeah, if a receiver successfully verifies a TLP LCRC checks out, sequence number is correct, it sends an acknowledgement, an ACK DLLP, back to the sender.
Thumbs up.
If there's an error, it sends a negative acknowledgement, an NAK DLLP.
Thumbs down.
Right. And when the sender gets that NAK, or if it doesn't receive an ACK within a specific time frame, that's a timeout, it automatically retransmits the TLP. It pulls it from its replay buffer.
And this just happens without software needing to step in.
Exactly. This whole process happens in the hardware, completely transparent to the software running on your system usually.
Yeah.
It's a really key hardware-based correction mechanism.
That sounds like a pretty robust system for catching and fixing errors right there on the link. But what about when data has to travel across multiple links, say, through a switch? That's where the transaction layer steps in, doesn't it?
Exactly right. The transaction layer focuses on the end-to-end reliability of the entire transaction, from the initial request all the way to the final response, potentially crossing multiple hops.
Okay.
Here we have the option of an end-to-end CRC or eCRC. This is a 32-bit CRC, but this one can be added by the component that starts the transaction, and it's checked only by the ultimate recipient.
So not checked at every hop like LCRC.
Correct. Think of LCRC like that quick checksum at each handoff.
The local check.
Yeah, the local cop. While eCRC is more like a final verification at the destination, making sure the whole journey was safe, it provides a safety net across the entire path, catching errors that maybe, just maybe, slipped past those hop-by-hop LCRC checks.
Gotcha. LCRC is the local cop on each street. eCRC is the detective checking everything at the final destination. What other error detection happens at this transaction layer level?
The transaction layer also looks for what are called malformed TLPs. These are packets that just don't follow the fundamental rules of how a TLP should be structured.
Like what?
Could be an incorrect packet type, maybe an incorrect length field, issues with the attribute fields within the packet. Basically, it doesn't look like a valid TLP.
Okay.
It also handles flow control protocol errors. These are problems with how components manage the credits they use to send data, making sure they don't overwhelm the receiver.
Right, the credit system.
Yeah. So, for instance, if a component doesn't receive updates on its available credits within a certain timeout period, that's flagged as a transaction layer error. And finally, there's something called data poisoning. There's a special bit in the TLP header, sometimes called the EDB or EP bit.
Error data bit.
Exactly. It can be set to indicate that the data payload might be corrupted somewhere along the way. The transaction layer is responsible for recognizing and handling these potentially tainted TLPs.
Okay, so PCIe has this really thoughtful, multi-layered approach to error detection, which makes perfect sense given the speeds involved. But what happens once an error is actually detected? That's where the classification comes in, right? Correctable, uncorrectable.
That's right. The PCIe specification categorizes errors based on how significantly they impact the system. What's the fallout?
Okay.
And this classification then determines how the error is handled. We start with correctable errors. These are the best case scenario because the system can usually recover without you even knowing.
So correctable errors, these are the little stumbles that the system catches itself on and fixes without causing a noticeable problem, like no data loss.
Precisely. These are errors that the PCIe hardware detects and fixes on its own, without any loss of data, without significant disruption to the system's basic operations. You might see a tiny dip in performance, maybe a little added latency because of a retransmission.
Like that async and A thing we talked about.
Exactly. But generally, the system just keeps humming along. The primary way these are corrected is through that ACNA protocol. If a bad TLP, maybe one with an LCRC error or a sequence number issue is received, it gets an NAK, sender retransmits from its buffer. Done.
Simple enough.
Same for a bad DLLP with a CRC error. It's simply discarded, the necessary DLLP gets resented. If a replay timer timeout occurs, sender doesn't get an ACK or NAK back in time, it just tries sending the TLP again.
Okay, so those sound like relatively minor issues handled pretty seamlessly at the hardware level. What other examples fall into this correctable category?
Well, we can also see a replay number rollover, which is just when the counter keeping track of retransmissions wraps around. Then there are receiver errors, which, as we mentioned, often originate at the physical layer, signal decoding issues, framing problems, that sort of thing.
Okay.
Sometimes a component might experience a corrected internal error. Something goes wrong inside the device itself, but gets fixed locally by its own internal magic.
Right.
And then there's something called header log overflow. Now, technically, this is a status of the error logging system itself, but it often pops up when maybe a whole bunch of uncorrectable errors are happening quickly.
Got it. And even though these are corrected by the hardware, they still get reported, right? Especially if you have that advanced error reporting AER enabled.
Exactly. That's a key point. When AER is active, the device that detects a correctable error will typically send an error core message up to the root port.
Error core for correctable.
Right. Then the system software, like the AER driver in Linux, logs these events. It's not about immediate recovery. Hardware already did that, but it's really valuable for monitoring trends.
Like seeing if one device keeps having corrected errors.
Precisely. A high frequency of correctable errors, even though they're being fixed, can be an early warning sign. Maybe a dodgy cable, a loose connection, maybe even a power supply issue starting to show. Monitoring these logs helps predict potential failures before they become serious problems.
Like your car's check engine light coming on intermittently.
Exactly. It's telling you something might need attention down the line, even if the car still drives fine for now.
That makes perfect sense, getting a heads up. Now, let's move on to the less desirable side. Uncorrectable errors. The ones hardware can't fix.
That's right. These inevitably lead to data loss, at least for the transaction that was in progress, and they can definitely impact system stability. They're split into two subcategories, non-fatal and fatal.
Okay, let's start with non-fatal uncorrectable errors. What's the story there?
With a non-fatal uncorrectable error, data is lost or corrupted for a specific transaction. But, and this is key, the PCIe link itself generally remains operational. Other ongoing transactions usually aren't affected directly.
So the communication pathway isn't totally broken?
Usually not. If any recovery is possible, it typically involves device-specific software related to the component that initiated or was targeted by the failed transaction. The PCIe link itself usually doesn't need a reset, but the system software is definitely notified.
So the OS knows something went wrong. What are some examples of these non-fatal errors?
Okay, common ones include receiving a poisoned TLP, that packet with the error bit set, indicating likely corrupt data.
Right.
Then there's an unsupported request, or UR. That's when a device gets a request it just doesn't understand or isn't designed to handle.
Okay.
A completion timeout, CTO, happens when a requester sends out a request but never gets a response back within the expected time.
Just left hanging.
Pretty much. A completer abort, or CA, is when a device gets a valid request but simply can't fulfill it due to some internal problem or invalid state. An unexpected completion that's getting a response that doesn't match any request you actually sent out. An ECRC error status means that end-to-end check failed, suggesting corruption somewhere along the multi-hop path. We also have access control services, ACS, violations related to rules for peer-to-peer traffic, and internal uncorrected errors within a component, plus errors during multicast, called MC-blocked TLPs.
Okay, definitely more serious than correctable since data is lost, but the link itself might survive. What about fatal uncorrectable errors? That sounds, well, fatal.
It is severe. Fatal uncorrectable errors mean the integrity of the PCIe link itself is compromised. It's no longer considered reliable for any communication.
So the whole connection is broken?
Essentially, yes. Not only is data lost for the transaction that failed, but subsequent transactions are also likely to fail or be corrupted. Recovery here usually requires significant system intervention.
Like what?
Resetting the component that detected the error, resetting the link it's connected to. Sometimes you might even need a full system reboot, or maybe even physically replacing the device via hot plug if the system supports it. The goal is to isolate the problem fast and stop it from causing more chaos.
Right. Prevent cascading failures.
Exactly. These errors signal a fundamental breakdown of the communication pathway itself.
What kind of errors are serious enough to be classified as fatal?
We're talking about really basic stuff going wrong. Malformed TLPs packets violating fundamental rules, like being way too big or having messed up formatting.
Okay.
Receiver overflow, getting data when you've already said you have no buffer space left, violating flow control.
Bad manners.
You could say that. Flow control protocol error, FCPE not getting those vital credit updates leading to a potential deadlock. Data link protocol error, a severe problem with the ASIC and AI protocol itself or other core link management. A surprise down error, the link just drops unexpectedly.
Yikes.
And while poison TLP is usually non-fatal, it can sometimes be configured or escalate to be treated as fatal in certain critical systems.
Okay, so the severity really dictates the response. From maybe just a software notification for non-fatal up to potentially needing a reboot for fatal. Now, you also mentioned something called advisory non-fatal errors, ANFE. Where do they fit in? Sounds a bit contradictory.
Yeah, ANFEs are an interesting category. They are specific types of non-fatal, uncorrectable errors, but they're reported in a, well, less severe way, hence advisory. Think of it as a softer notification.
Okay.
Common examples are unsupported requests, UR, and completer abort, CSCA, but only if the device completing the request is specifically configured to treat these as non-fatal in the first place.
So why have this different, less alarming way of reporting? What's the point of an ANFE?
The main idea is to let the system know about certain, let's say, expected non-critical error events without triggering the standard, possibly disruptive, uncorrectable error handling.
Like when?
Well, think about system boot up during configuration.
Yeah.
Software might probe a device, maybe try to access a function that isn't enabled yet or doesn't even exist on that specific model.
Right, that happens.
So the device responds with an unsupported request. That's technically an error, but it's expected in that context and doesn't mean the hardware is faulty. If that triggered a full non-fatal error alert every time.
It would be noisy and maybe cause unnecessary recovery attempts.
Exactly. By classifying it as an ANFE, the system can still log it if needed for tracking, but it avoids overreacting to what's often just part of normal setup or discovery.
Okay, so how are these ANFEs actually reported then, if they're technically uncorrectable but handled differently?
This is where it gets a bit nuanced and kind of interesting. A device that supports AER and is configured to treat, say, a UR as non-fatal and report it as an ANFE will actually signal this by sending an error core message.
Wait, the same message used for correctable errors?
Yep. The same error core message goes to the root port. Now, if the device doesn't support AER or if ANFE reporting isn't specifically enabled for that condition, it might not send any error message at all for that UR or CA.
Huh. So an uncorrectable situation gets reported using a correctable error message type sometimes.
Exactly. It seems counterintuitive, but it's all about trying to de-escalate the immediate system response for these specific, often anticipated, non-fatal scenarios. It prevents unnecessary alarm bells.
That's a clever, if slightly confusing, way to manage those expected bumps in the road. So all this intricate error detection and classification is happening down in the hardware. But how does the system, software, the OS, the firmware actually find out about these errors and do something? That's where advanced error reporting, AER, really shines, right?
Absolutely. It's like moving from basic idiot lights to a full diagnostic computer readout.
Giving you the who, what, when, where, and why of the error.
Precisely. While the basic error reporting in PCIe provides a fundamental signal, AER significantly enhances this with much greater detail. Standard reporting is pretty limited in what it tells you.
Okay.
AER, on the other hand, supplies a wealth of precise info about both correctable and uncorrectable errors. Things like the exact type of error, its configured severity level, and, crucially, you can even log the header of the transaction layer packet, TLP, that was involved in the error.
Ah, the packet itself.
Yeah, that header information is critical for digging into the root cause, isolating the problematic component, and even predicting future problems by tracking trends in those less severe correctable errors.
So monitoring correctable errors via AER can be like preventative maintenance?
Kind of, yeah. You can spot patterns. Maybe one device keeps getting receiver errors, indicating it might be starting to fail before it causes a major uncorrectable problem.
So AER is basically a more sophisticated diagnostic toolkit built into PCIe. How is it actually implemented in the hardware? Is it just more registers?
Essentially, yes. AER is implemented as a specific, standardized, extended capability structure within the PCIe configuration space of a device.
Config space, that's where the system learns about the device's features.
Exactly. And the AER capability is a dedicated block of registers within that space. These registers handle all the AER functions, storing the status of detected errors, allowing the system to mask certain errors from being reported.
Masking, so you can ignore certain errors if you want.
You can tell the hardware not to report them via AER messages, yes. The registers also let you set the severity for uncorrectable types, control the overall AER operation, capture and store that TLP header we mentioned, and even identify the source of errors, especially within root ports.
Okay. And does it just work automatically?
No, that's important. AER isn't typically active by default. Device drivers or the system firmware need to explicitly enable and configure it. Operating systems usually provide standard ways for drivers to do this, like function calls.
Gotcha. So it's the set of registers giving a much deeper view. What are some of the key registers in there? What info do they hold?
Okay, several crucial ones. First, the uncorrectable error status register. This has individual bits that get set when different uncorrectable errors happen. Data link error, poison TLP, flow control error, unsupported request, etc.
1 bit per error type.
Yep. And it's usually read-write 1 to clear, or RW1C. Software reads it, sees the error, processes it, then writes a 1 back to that bit to clear it.
Acknowledging the error.
Right. Then you have the uncorrectable error mask register. This lets the OS selectively disable the reporting for specific uncorrectable errors. If a bit is set here, the corresponding error in the status register won't trigger an AER message.
So you can tune the reporting.
Exactly. And similarly, the uncorrectable error severity register lets you configure each type of uncorrectable error as either non-fatal or fatal. Again, the bits line up with the status register.
Okay, so those 3 work together. Status says what happened, mask says if we report it, severity says how bad we consider it. What about correctable errors? Similar setup.
Yes, parallel structure. There's a correctable error status register that logs specific correctable errors, receiver error, bad TLP, replay, timer, timeout, etc. Also typically RW1C.
Okay.
And a correctable error mask register to selectively disable reporting of specific correctable error types if they become too noisy, for instance.
Right. And getting back to uncorrectable errors, you mentioned the header log. That sounds super useful for debugging.
Oh, it is. The header log registers usually 4 32-bit registers. Capture and store the 16-byte TLP header of the very first uncorrectable error that occurs after the log is cleared.
The first one. How do you know which error it belongs to?
Good question. There's another register, the Advanced Error Capabilities and Control Register. It contains a first error pointer, FEP, that points to the specific bit in their uncorrectable error status register that corresponds to the error whose header got logged.
Ah, connects the log to the status bit.
Exactly. That control register also has bits for enabling ECRC generation checking and just indicating if the header log is even present on this device. That logged header is gold for debugging, shows the packet type, address, source and destination IDs.
A real snapshot of the crime scene. What about the root port? Since it's kind of the traffic cop for a PCIe tree, does it have special AER registers?
It does. The root port, managing communication downstream, has its own specific AER registers. There's the root error command register, which lets the OS enable or disable the root port's ability to generate system interrupts like MSI or legacy INTX when it receives those error fatal messages from devices below it.
So the root port can signal the CPU.
Precisely. Then the root error status register logs which types of error messages it has received and also if any errors were detected by the root port itself. It tracks if error and fatal messages came in and if multiple errors occurred.
Okay.
And crucially, the error source identification register in the root port captures the requester ID, the bus, device, and function number of the specific device that sent the error message. This is absolutely vital for figuring out which device is complaining in a potentially complex system.
Okay, so the root port acts as the central collection agency for error reports in its domain. Let's trace the flow then. An error happens in an endpoint device. How does that info get all the way up to the OS so it can react?
Right, it's a multi-stage journey. First, the device detects an error. Hardware logic.
Step 1.
It records the details internally in its AER registers, sets the status bit, maybe logs the header if it's the first uncorrectable one. Then, if AER is enabled for this device, and if this specific error type isn't masked,
the ifs.
Right. Then the device generates the appropriate error message, error core, earn and fatal, or error fatal, and sends it as a special message packet upstream towards the root port.
Okay, message travels up the tree.
The root port receives this message. It logs the event in its own root error status register, captures the sender ID in the source ID register.
Step 4.
And, if configured via the root error command register, it generates a system interrupt, poking the CPU.
Waking up the OS.
Exactly. That interrupt signals the OS. An AER driver, or a general hardware error handler like WHEA in Windows, wakes up.
Software takes over.
Right. The software driver typically starts by reading the root port's registers. Okay, who reported an error?
Yeah.
It gets the source ID.
Finds the culprit.
Then, using that ID, it can talk directly to the reporting device. It reads its detailed AER status registers, maybe grabs the header log contents to get the full picture.
Gets the full story.
And finally, based on the severity, correctable, non-fatal, fatal, and the specific type of error reported, the OS takes action. Could be just logging it, could be trying to reset the device or link, could be telling the user there's a serious problem, maybe even initiating a controlled shutdown for a fatal error.
That makes perfect sense. Hardware detects and logs locally, signals the root port, root port aggregates and interrupts, OS driver investigates and acts. Now, you mentioned earlier that an error core message itself doesn't tell you the specific type of correctable error. How does the system figure out that subclass?
That's a really important detail. Yeah, the error core message itself is just a generic flag, hey, I fixed something.
Okay.
To find out the specific nature of that correctable error, the subclass, the system software, needs to go read the correctable error status register back on the device that sent the error core message.
Back to the source device's registers.
Exactly. That register, as we said, has individual status bits, one for receiver error, one for bad TLP, one for bad DLLP, replay timer timeout, maybe even that advisory non-fatal error bit.
So the OS reads that register, sees which bit is set,
And knows exactly what kind of correctable hiccup occurred. Was it a link level retry, a physical layer issue, an ANFE being reported gently?
Gotcha. The error core is the alert. The correctable error status register has the specifics. Now, even though the error was already fixed by hardware, why does the system still care about these specific subclasses? Seems like overkill if it's already handled.
It might seem that way, but knowing the specific type is still really valuable for a few reasons. First, performance diagnostics. Different correctable errors can impact performance differently. Lots of bad TLPs causing retransmissions adds latency, right?
Sure.
Second, predictive failure analysis. If you start seeing a trend, maybe a specific device logs more and more receiver errors over time, that's a strong hint that the physical connection or the device itself might be degrading. It lets you potentially replace it before it causes uncorrectable errors.
Proactive maintenance based on trends.
Exactly. And third, just for debugging and fault isolation, understanding the nature of the corrected event helps engineers track down subtle hardware or firmware bugs. Seeing the ANFE status bit tells you it was likely an expected UR during probing, not some random glitch. So yeah, even though they're corrected, knowing the subclass gives valuable insight into the link's health and potential future issues.
That's really helpful understanding that level of detail. So we've got the hardware doing detection and AER providing the detailed reports. But how do the actual system players, the OS and the firmware, the BIOS UEFI, coordinate all this? It's clearly not just hardware alone.
Absolutely not. It's a real team effort. Hardware, system firmware, BIOS Wi-Fi, and the operating system all have distinct, crucial roles in robust PCIe error handling.
Okay, let's start with the firmware then. What's its role in this?
Well, during the initial boot process, the firmware does the basic heavy lifting, initializing the PCI devices, setting up the links, and it can configure some very basic error reporting settings.
Setting the stage.
Pretty much. But for the advanced stuff, especially AER, the operating system usually needs to take over control once it boots. There's a standard way they talk using ACPI.
That configuration interface.
Right. Using a method called OSC, Operating System Capabilities, the OS basically tells the firmware, hey, I want to manage PCIe error reporting features now.
Asking for the keys.
Exactly. If the firmware grants this control, and it usually does on modern systems, then the OS's AER driver can fully manage the reporting, masking, severity settings, and recovery. If that handover doesn't happen correctly, maybe due to older firmware or configuration issues, it can limit the OS's ability to use AER effectively.
Okay. What else does firmware do?
Critically, the firmware describes the system's hardware error sources to the OS. This includes telling the OS where the PCIe root port AER capabilities are located in memory or config space. It does this using ACPI tables, like the ACSIC hardware error source table. This lets the OS discover and manage the platform's specific error hardware consistently.
So, firmware does initial setup and tells the OS what hardware is available for error handling. Then the OS takes over for the advanced management. Let's dive into the OS side. How do different systems like Linux and Windows handle these reported errors?
Both have pretty comprehensive frameworks. In Linux, you've got that dedicated kernel driver. Same.
All right, you mentioned that.
Its job is to collect the detailed AER info, report it via system logs, like DMESG, and try to initiate recovery. It usually hooks into AER-capable root ports.
Okay.
When an error comes in, CER typically logs warnings for correctable errors and more serious error messages for uncorrectable ones. For recovery, it might just clear the status for correctable ones. For uncorrectable, it often notifies the specific driver for the affected device, saying, hey, your device had an error, and might try to reset the PCIe link itself, depending on the severity.
So it tries to handle things automatically.
It attempts to, yeah. And you can explicitly enable AER reporting using kernel functions like Sanaplepsia reporting. Linux also often includes support for error injection for testing.
Ah, good for developers.
Definitely. And there are user space tools like Rasman that can collect and monitor AER events over time.
Sounds pretty robust. What about Windows? How does it approach this?
Windows uses a broader framework called WHEA, the Windows Hardware Error Architecture.
Okay.
WHEA is designed to handle all sorts of hardware errors, not just PCIe, in a standardized way. It definitely understands and uses the detailed info from AER when available.
Does it use specific drivers, too?
Yes, it relies on something called PSHEDs, platform-specific hardware error drivers. These are plugins that understand the specific error reporting details of the underlying hardware platform, including how to interact with AER registers.
Got it. So WHEA is the framework, PSHEDs are the platform specifics?
Right. When a PCI error reported via AER or otherwise occurs, WHEA logs it in the standard Windows system event log. You might see entries from PCI Express root port, for example. It can also use ETW event tracing for Windows to notify other components.
And recovery.
Based on the error details, WHEA processes it, logs it, and may initiate recovery actions, potentially involving the PSHED or specific device drivers.
Yeah.
It's worth noting that while masking is done in hardware via AER registers, if Windows receives an error report, it generally processes it. There have actually been some weird cases reported where even a correctable error, once reported up to Windows, triggered a blue screen of death on certain systems.
Really? A correctable error causing a BSOD?
It highlights that the interaction between hardware reporting and the OS response can sometimes have complex, unexpected outcomes, even for theoretically harmless errors.
Interesting. And briefly, what about other OCs like FreeBSD? Similar approaches.
Yeah, FreeBSD also has support for AER. There's work there to expose the AER registers via system interfaces, maybe similar to how it handles machine check errors. Tools exist for reading AER registers and injecting errors too. And similar to Linux, some FreeBSD users have found the sheer volume of correctable error messages can sometimes be overwhelming. So there are ways, like kernel parameters, PCI and OR, to disable AER reporting if it becomes too noisy for a particular setup.
So it really is this intricate dance between the hardware detecting, AER providing details, firmware setting the stage, and the OS interpreting and reacting, a true collaborative system.
Absolutely. Hardware does the frontline detection and logging. Firmware initializes and describes the capabilities. The OS takes control, uses mechanisms like AER to get the deep details, logs everything, notifies admins or other software, and orchestrates recovery based on what it finds out. That clean handover of control from firmware to OS is really vital for it all to work smoothly.
Well, we have certainly taken a deep dive into the complex and a really critical world of PCIe error detection and handling today. It's pretty amazing how many layers of protection are built into this fundamental tech to keep our systems reliable.
It really is.
Yeah.
We've seen that sophisticated, multi-layered approach, physical, data link, transaction layers all playing a part. We've looked at the error classifications, correctable, the uncorrectable non-fatal and fatal types, and those interesting advisory non-fatal ones.
Right.
And we've definitely highlighted how crucial advanced error reporting, AER, is for getting that detailed diagnostic info needed for smart error management and even predictive maintenance by the OS.
And understanding these mechanisms, even at a high level, really gives you a deeper appreciation for how robust modern computing aims to be. It kind of demystifies those random glitches sometimes, knowing all this work is happening constantly behind the scenes.
Precisely. So maybe a final thought for you to ponder. As we push interconnects to even higher speeds, more complexity, think future compute, AI, autonomous systems. How does error handling itself need to evolve?
Good question.
How do we maintain reliability at, say, PCIe 7.0 speeds and beyond, especially in applications where an error isn't just inconvenient but potentially dangerous? What new challenges pop up with tighter integration and insane bandwidth demands? It's clear that innovation in error management has to keep pace with the raw speed improvements.